just put into the chat. Excellent. Okay, I just put into the chat that this is designed to be a discussion kind of meeting. Does not need to be me talking all the time. So if you hit something and you want to answer a question or something like that, absolutely feel free to go ahead and just unmute yourself to join in. Many of you may have seen this cartoon. It's out there all over the place. We had to be careful to not get copyrighted stuff, so I just created it. But it's the -1 telling pi to get rational and pi responding, get real. Knowing that when we look at these things, we start thinking of the number categories. We want to be thinking about why is it that we study this, right? We talk to our students, we have them do calculations and things, and we often start with our whole numbers and then move into fractions and decimals, those things, you know, when we're in the A and B and maybe C CCRS levels. But I don't think we make as strong a connection between the different number categories as we could to help us get them to understand why certain rules work for integers or why certain things work for fractions. So we often do go through, I go through and really want to be careful in making sure that students are understanding those. So we're going to look at these different number calculations today, or classifications today, and including a little bit of algebra. That's not really one of our number classifications, but it is there. And we're going to keep going on and linking into the other number systems as we go. So I put into here standards aligned. My God, there's a lot of them. I couldn't list them all. So I kind of started grouping them together, but we are hitting concepts that are in all 5 of the levels in CCRS from A to E. And we're going to look pretty strongly at mathematical practice 7, a little bit in mathematical practice 2, but not quite. I know you don't have to read the whole page here because this is straight out of our CCRS manual. But the important parts here is the students look closely and discern things, and that they shift their perspective, that they think how things are the same and how things are different when we're looking at these numbers in different number categories. So the structure of the mathematical categories is often very similar, if not the same. And our big thing is to get students to understand why. If any of you have read through the Singapore math book that talks about why before how, it's really nice to get our students just thinking about the concepts of what we're doing. And those of you that were in the Math Institute with Dan Meyer that we had, and he talked a lot about mathematics being the cure to the headache. But we got to help the students to understand that they have the headache first and then build the correction for that too. So we're going to start out with a common number diagram that many of you may have seen or used, but I just want to start this out. Go ahead and unmute and bring it up. What do you notice and what do you wonder about this picture?
I see a couple people have unmuted. Tracy, did you want to add something?
I guess I don't really know what that is. I've never used it before. I see a bunch of ovals.
Okay. Nice there. Okay, so you notice that there's ovals. Helen brought in something about what goes in the middle and what covers all. I think that's a good observation, that there's some sort of leveling or inside of other things type of ideas in this diagram. Anybody else have anything else?
I wonder why the ovals, oops. I wonder why the ovals in the center don't go all the way on the right to touch the outside.
Yeah, so some of the ovals are bigger and some of them are smaller, right? Okay, so I think this is a great thing to notice and wonder.
Yeah, I noticed that too, like the bigger two touch on the right side and then the smaller two touch on the right side, but then there's a little space in there.
There is. And that may have been a little bit of a mistake that I meant to have those all the way over and didn't quite get them where I wanted them to be. But here's the categorization as to how we normally talk about our number systems. So we start out with the counting numbers, and that's in our level A stuff that we look in the CCRS, being able to add and subtract with digits up through 10, and then going into the adding and subtracting up through 20, and knowing those values of what they mean, and starting to get a concept even in the level A of measuring something as units of a chunk. And so I can count that a desk is 7 or 8 paper clips long or something like that, right? Just getting the idea of counting and things that I can physically hold in my hand, a counting or a natural number. And then we extended out to the whole numbers, and the whole numbers are simply just all the counting numbers, 1, 2, 3, and etc. Plus that 0. Lindsay just chatted into there a really good question we'd like to know is kind of where are you teaching? What materials are you teaching? Because we can adjust a little bit of what we're saying in this to hit the levels that you are. And then the integers are simply all of, oh, nice, Rebecca. I love that we're introducing irrationals. The integers are those numbers that are the counting numbers, 1, 2, 3, 4, etc. And their opposites, so -1, -2, -3, and including 0, which is that whole number, and then out to the rational numbers where they can be written as a ratio. Excellent. I haven't taught much math yet. Well, this is a good place for us to start. We talked a lot about the ovals. We didn't talk much about the rectangles. Anybody notice or want to see something or ask any questions about what those rectangles are? And why they're rectangular?
That was my question. Why are they rectangles?
Because those are the things we get that are a little bit different. All of those ovals, they're all different aspects of the same concept of numbers. But yes, Rebecca, they have their own category, and they're separated out. They're not nested in with the other things. So we'll get up and we'll talk a little bit about those. We're not going to get a whole lot into the imaginary numbers or complex numbers. We're going to touch on that just a little bit, but focus more in the reals. Okay, so a different number diagram, if you want to use this one as well, and you'll get a copy of this this presentation, so you can copy these, use them to your heart's content, it's fine. Notice how the natural numbers have an arrow moving up into the whole numbers, which moves up into the integers, which moves up into the rationals. So each of these builds into the next concept, and all of those build up into the real numbers. But then we got that oddball kind of off to the right-hand side, the irrational numbers. And the irrational numbers are also part of the reals, but they are not part of the rationals. They are separate. So this sounds just way easy, right? It's just numbers. Why do we have to categorize them or have different things about them? The common thing that we run into is that a lot of our students really don't understand these. Okay, no, show the categories. Okay. But a lot of our students that come in, they got a pretty good hold on the whole numbers, and they can add and they can subtract and they can multiply and they can divide and everything's comfy dory. But then they start getting into fractions and they start freaking out. Or we start talking about the algebra and they get confused with algebra. All of a sudden you're bringing in letters in the middle of our number systems. What the heck's going on? If we can get our students to truly understand, truly look at the concept of what these numbers are and how they are connected to each other, it makes those things like fractions and algebra and integers easier, right? So important thing to remember is, just like we talk about with the geometric shapes, all of the shapes that are more specific have the same concepts as the shapes that are less specific. So every rectangle is a parallelogram. Well, every counting number is an integer, right? So anything that's true about counting numbers has to be true about integers. But not everything that's true about integers has to be true about counting numbers, because there's stuff that's outside. So if we start with whole numbers and work our way out to the real numbers, we can think of building scaffolding to help our students move from a basic understanding of some of the math that they do up to those higher CCRS standards and really understand how you move from one to the next. The one thing that I don't like, and this is just a personal thing with me, the CCRS does it too. They start bringing in all of the rational numbers and talking about fractions and decimals and percents and all that stuff. And then they save those integers until they get all the way out in algebra. On a personal level, I just think that's wrong, because the integers are an interior category to the rational numbers. So for me, I always teach those first. And if we build this up with this scaffolding, students will get it, right? They'll start to understand as we build it in. So very first thing in math, and this was some of the first things that humans started to think about when they started thinking about numbers, is if I add stuff, I can only add stuff that is the same stuff and get the same stuff out of it, right? It's what we call mathematical closure. And mathematical closure was one of the most important concepts that we started to build into our number system in those early civilizations. Getting people to understand that I can't break this. I can't get something that is not the same thing. And yes, integers are a struggle. Yes. So I like to get those early, because then when we get to graphs, it's not as big of a deal. So the secondary math rule that I like to talk about, and this is one of our concepts, is the one I was talking about that's kind of mathematical practice too, that reasoning abstractly and quantitatively, but it's more reasoning in composition and decomposition. Numbers don't exist by themselves. Any number that you can create, I can break it into other numbers that would have the same rational value. The reason for that is some numbers are a little bit easier to deal with, and some of them are maybe not so easy to deal with. So I will bring students in and I'll just list the numbers 0 through 12 and have them right next to them. Like, this is really easy for me to multiply by, and this is a little bit, maybe not quite so easy. And then these ones are hard for me, right? And try to build that concept, because almost everybody will say that 1 and 2 is really easy. 3 and 4, yeah, they're usually pretty easy, not too bad, maybe a little bit of but they're okay. And all of a sudden 5 becomes easy again. And then 6, 7, 8, and 9 get a little bit trickier. And all of a sudden 10's super easy, right? So if we can rationalize the idea of pulling those numbers into their number categories and composing and decomposing numbers, we get students to understand truly what's going on. And I brought in here that my students do this carry and borrow thing. One of the first things I do in class is say, I don't use the words carry and borrow. I just think it's a bad way to discuss the concept of what we're doing. So I like to use the word exchange. And the exchange we can also think about as composition, decomposition, but the students don't like those words. They like exchange. It makes sense. So if we can get them to know those two main rules, you can only add or subtract, well, actually, sorry, with add, you can only add the same numbers to the same numbers and get the same numbers. You can only add the same things to the same things and get the same things. And so adding a number value and composing tens is where we're getting that carry thing. But if I think about, if I had 7 $1 bills and someone gave me 8 $1 bills, I don't all of a sudden have a 10 and $5 bills. I don't have that. I have 15 $1 bills. So ones plus ones can only give me ones. That's the only thing that's even possible. But once I've got ones, then I can exchange 10 ones for 1 10 and start to talk about a 10 and a 5 giving me 15. So somebody's bringing up the chat here. Sorry, we're going to grab that really quick. The numbers 0 through 12, which are most comfortable. Yeah. So the nice thing is just try to make these things easy. I get a lot of these expressions when we start doing that. Oh my God, that's so easy. Why didn't I get taught this before? Right? Most likely they did, but they didn't maybe necessarily internalize some of that teaching they had in their elementary school. Oh, cash drawer is awesome, Luella. I love that concept. I have a lot of like little fake denominations, monopoly money type of stuff, and use that with them to talk them through it. So let's start, right? And start with the easiest thing, the counting numbers. So if we got 5 plus 2, that is, of course, what value? Yeah, 5 plus 2 gives us the 7, right? And then when we start hitting 8 plus 7, all of a sudden it looks a little bit different because I don't get that nice, easy, just single digit value. I get a number that all of a sudden looks a little bit different, right? We get a 5, but all of a sudden we've got this extra 1 out there in the tens column. And if we help them to realize, well, wait a minute, 8 plus 7 is exactly the same as 8 plus 2. If I recognize, I'm also going to add 5 to that as well. So 8 plus 2 would be that composition of 10. Any of you that went to the trainings by Jim Brickwoody a few years ago, this is some of the stuff that he does in there too, to help us get that thing. Compose the 10 and then just see what's left over when you've got that. The 9 minus 3 is, of course, what value? Okay, yeah, Tracy, 6, right? And the students will, they'll do this and okay, it's 1, 2, okay, that's 4 and 2, that's 6, right? I mean, they can count them off on their fingers and get the idea. Sounds pretty easy. But what about this 14 minus 6? Like, how does that work? For a lot of students, if we tried to follow those trainings that we did as elementary school students, right? We cross off the 10s, drop it by 1 value and add 10 to the 1s. We're right back where we started. right? It's exactly the same thing. The borrow or the exchange in that case really doesn't help us. But if we can see that 14, the 14 minus 6 is the same as 14 minus 4, but if I've taken away 4, I haven't taken away everything I need to take away. So I take away 2 more. And when I do the 14 minus 4, of course, that's 10. And the 10 take away 2, most of the students grab that one really easy. But it's very common for me to see like 14 minus 6, that's 6, or something like that. Students want to just grab it and try to run with it fast. Do I write it in 2 steps like that? Sometimes I do, yes. Yes, I agree with that, Luella. Same thing. Why did you do that? Right? Not just do it, but why did that work? Of course, with these ones, right? This is that level A standard of being able to add and subtract within 20. That most of the students are not going to have a problem with this. 14 minus 6. It's very seldom that I don't get 8, but I could end up getting 8. But if we go, okay, go. Slide control. Okay, I think it's because I was annotating, it doesn't want to move. So let me clear all my annotations. Move on. Okay, Lindsay or Marissa, can you tell me why this isn't moving? This should be moving.
That is very strange. Okay, so you cleared annotations.
Good.
Um,
And we'll just slideshow back in.
do you have to press the arrow again in the controls instead of annotate? Like there's a like you're selecting the cursor
There
again?
it goes.
Okay.
Okay, there we go. Now we got it. So yeah, Luella, I think this ties in really closely to what you were talking about when we start getting those values that aren't just within the 20. When we start getting into the B standards and C standards, moving up to within 100 and within 1,000. And I just jumped over the hundreds, went straight to the thousands. But if we add 736 to 251, what do we get? Yeah, 987, right? But the easy way to get the students to really start thinking about, like, I know what it is, right? I don't need to know this, but you think, okay, think about what you're doing here because it's going to help you in the next problem. It's that we can only add the same stuff to the same stuff and get the same stuff. So if I add 6 ones to 1 1, I have to get 7 ones. If I add 3 10s to 5 10s, I have to get 8 10s. I can't get 8 100s or anything like that. So I can only add within my number placements and get the same value in the number placements. And I'm sorry, I put blocks over this to try and move them, but when I'm in slideshow mode, it won't let me move the blocks. But yes, we get the 987. Yes, I do that too, Luella. That's a really good one. I should have put that into here. Say 700 plus 30 plus 6 and the 200 plus 50 plus 7, or sorry, plus 1 to give us 7. But when we're doing those things and we are separating them out to get them to see those concepts, this makes a direct connection right there to our polynomials that we end up with in algebra, right? I can only add x squareds to x squareds and get x squareds. If I add x squareds to x squareds, I do not get x to the 4ths. So if they truly understand what's going on here in the basic counting and whole numbers of math, then they really start to understand the polynomials, which is a level E standard. A.APR1 says, understand that polynomials are analogous to integers. So we're building from a level B concept towards a level E concept. You know, that's the connection we want to make to help them to really understand this. But now comes the one that usually starts to get them thinking that, you know, something's got to be hard, or they know how to do it, but they don't necessarily know why they're doing it the way they're doing it. What do we do if we have that 846 plus 579? Okay, and what I'll do to help the students see it is I'll say this is 15, and this is 11, and this is 13, right? They see those 13 100s, 11 10s, and 15 1s. And they all start to get really, really, really mad at me. Because they're like, you can't write 15 down there. You got to write the 5 and carry the 1. But if they can see that really what truly is going on here is 6 1s plus 9 1s is 15 1s. And then we remove 10 1s and are left with 5 1s, but we add 1 in the tens column, which of course will give us 12 10s. But if we remove 10 10s, we get 2 10s, but we add 1 more 100, because they all know if I take 10 $10 bills, it spends exactly the same as one $100 bill. And they all say, well, how come I don't have a $100 bill? I want to have one. Never seen a $100 bill, right? But we get those, and of course we get 14 hundreds, but we subtract 10 100s, which leaves us with 4 100s, and we get 1 more up there in the thousands, but there weren't any thousands to put it with. So we get the 1,425 for the value when we do that. But part of the reason that I really want them to get a good, solid understanding of the why this works is because of that coming up in level E algebra, when they have 8x squareds plus 4x's plus 6 and 5x squareds plus 7x's plus 9, and they get 15 out here. Sorry, and started to do the wrong, looking at the wrong one and writing at the same time that I'm doing it. My brain works faster than my mouth does. We got 11 x's and of course 13x squareds. That you can't do that compose decompose. I can't take 10 from the 15, write it as 5, and carry 10 into the next column. It doesn't work because they're not all 10s, they're all x's. It's the base x. This also helps them to understand when we get into the algebra with that 8x squared and 4x and 6 and stuff, why do we write the polynomials in descending order, right? We get that highest degree x squareds, then we write our x's, then we write our constants at the end, because it's exactly the same way we write our numbers. We write hundreds before we write tens, before we write ones. So the big part of it is why, right? It's that idea of understand why. And I agree, Lindsay, I get the same thing. I get the students go, well, my God, why wasn't I ever shown this before? They probably were, right? But again, it's been years since you've been in elementary school. and you may not have truly understood it back then. And it just makes so much more sense now that you're old enough to pay closer attention to it. Of course, the 475 minus 423 is really easy because they all subtract really easily, right? 1 does subtract from 4, and 7 does, or 2 does subtract from 7, and 3 does subtract from 5. But what about when we've got those numbers that don't subtract as easily? You know, I've got 4, and I'm supposed to take away, or I'm supposed to remove 5. Well, that doesn't work. I can't take 5 away from 4, right? So they get into there and they know the rule, but help them to see, why does this rule work? Sorry, I'm just erasing all the extra stuff out here. Okay. If we think of this and we do that rule that we've all been taught, cross out the 9, make it an 8, make this 16, cross out the 16, make this 15, make this 14. But we state you have taken 9 100s and made it into 8 100s. Now, if you had 9 $100 bills in your pocket and all of a sudden one of them was missing and you only had 8 $100 bills, you'd be really ticked off, right? I'd have to figure out what the heck happened to my $100 bill. That's a lot of money. But if I think about the idea that I just went to the bank teller and I exchanged 1 $100 bill for 10 $10 bills, I used to have 6 $10 bills. I now have 16 of them because I just got 10 more. And that's where that borrow thing really starts to make sense. You know, why is it that we cross out and move down? And then the 14 minus 5 right here, we'll really look at that as 14 minus 4, because that is so much easier, right? I love 14 minus 4. That's a really easy subtraction. Of course, that gives me 10. But I know if I've only subtracted 4 and I'm supposed to subtract 5, I got to take 1 more off. And of course, that gives me 9, right? Now we can do 14 minus 5 is 9, and the students get it and they're just fine. But if they think through that idea of do easy subtractions, they get to where I tell them, you know, you can use this lovely machine. You know, we've got these calculators, they are available to them on the GD test. But in a lot of cases, you can do this faster in your brain than you can do it on a calculator if you're truly understanding why everything works. Okay. Anybody have any questions over what we've talked about on this slide? I know we took a lot of time here, but this is a foundation that I like to really lay for my students to make sure they're really understanding it. Everybody good? Okay, great. Okay, let me try this again. Every time I want to draw, it wants to start not allowing me to move on. Marissa, can you move me on? I did give you rights to move. Thank you. I have to try and see why it's doing that. But anyway, of course, we can also talk about this on the number line, and someone had brought that up. Yes, do the number line. Yes, Lindsay, thank you. Please do interrupt with questions. I want this to be a discussion, right? That really helps. And we've had a lot of good things come in on the chat. Thank you. If we talk about counting and whole numbers, there's something in it that if we add them, they have to give us other counting or whole numbers, right? If I'm moving on that number line and I have 5 plus 3 equaling 8, I can think, well, if I just take 5 and I go 3 more, that's 6, 7, 8, I can get those, right? And adding whole numbers to whole numbers has to give us whole numbers. That was that mathematical closure that we talked about. Okay, Lindsay, go ahead and move on. Or Marissa, thank you. And then if we're going into bigger numbers, the 57 plus 36. This is a lot of what your elementary schools are being taught now, because this is in our CCRS standards of being able to decompose and recompose numbers to make these additions easier. So if I've got to add 57 to 36, our old way, the way that we were taught, the way I was taught too, is you got to take that 3 or that 7 plus 6 and get 13 and carry the 1 into the tens column and all that stuff. But if we just recognize, hey, wait a minute, that's 50 and 30. I know I've got that 7 and 6 out there. I'm still going to deal with those. But when you go to the grocery store or Target or something like that, and they're counting your money back to you, they don't start saying, here's a penny and here's another penny and here's another penny. Now here's a nickel. Now here's a quarter. Now here's $1. Here's another $1. Oh, now here's a 5, right? They never do that. They give you the big stuff first. So if we're looking in that whole numbers area, we think 57 plus 36, well, that's just 50 and 30. That's easy. That's 80. I got that one right off the top, didn't even have to think about it. But then I've got that 7 and 6. Now I can continue and say 80 plus the 7 gives me 87, and 87 plus 6 more, well, that moves me all the way up to 93, and I got that. But if we do, again, that composition decomposition thing, I can see that 6 can be broken into 3 and 3. And the students will often ask, well, why did you choose 3? It's because I see that 7, right? Grab that 7, find what I call its tens buddy. Okay, so you find those numbers that help it to make 10 easily, because 10 is like the greatest number ever. It is so easy to deal with. So if I recognize that the tens buddy to 7 is 3, then I can see 6 is 3 plus 3, because then 7 plus 3 gives me 10. And of course, the 80 plus 10 gives me 90. And I still got those 3 more. This is the stuff that you see out on the internet of parents going berserk of why the bleep are they teaching this to my kids? Just teach them the way I taught. They don't have to learn all this new math. Well, this isn't new math. This is old math. This is math that we've known since back in the Greeks, right? It all still works. It's all beneficial. And students, when they start to do this, get a little bit more comfortable with the idea of, you know what, I can come up with this answer without having to grab my calculator. Okay, go ahead and move on. Thank you. The issue is then when we hit subtraction. So the students all will get, and I mean, they learned back in first grade, 5 minus 3. Well, of course, that's just 2. It's going out 5, going backwards 3. I end up at 2. And subtracting a whole number from a whole number gave me a whole number. But if I switch that order, if I don't have 5 minus 3, I got 3 minus 5. All of a sudden now, I don't have a whole number anymore. And mathematics, it's broken. Like we just broke math. It doesn't work anymore. So what the Greeks and the other early civilizations looked at was saying, well, wait a minute, mathematics has to be closed. We want closure. We want things to work. So if they don't work in the idea of getting these numbers back out, that I get a number 0, 1, 2, 3, 4, 5, etc. If that doesn't work, then I need to create something new. Yeah, there you go, Patsy. We broke math. But, if it doesn't work, then we need to change our viewpoint on what numbers truly are. And of course, this is where we start to get the integers. Now I've put these symbols into there, those squiggly brackets in there, those are called a set, okay? And so we'll often talk about categories of numbers as a set. And so the counting numbers, which that's what I learned. I got taught counting. They're also called the natural numbers because they're things we see in nature. So that's why that counting number is listed as the set N. And of course, the whole numbers W is listed as the whole W. But integers seems awfully weird that all of a sudden we throw Z in, right? Shouldn't integers be I? When they started creating these number systems and thinking of these things in categories of how they work, they would have started to think, well, wait a minute, integers, we can just call those I. But later on, we all of a sudden came up with this new category called irrationals. And all of a sudden, I didn't work so well anymore because I don't know which I I'm talking about. So there's no particular reason they chose Z, they just did. But the set Z is introduced because subtraction is not closed on counting numbers and whole numbers. So we just create a new category where it is, and we just make it work. We define the integers set Z. Oh, well, thank you, Rebecca. I actually did not know that. Z is for Zalen. Awesome. Everybody note that down, the chat that Rebecca just put in. I didn't research that and I didn't get it. So, well, okay, now she's walking it back. I think that's true. But yes, I think that's great, Rebecca. Thank you. But we define the integer Z as the whole numbers and their opposites, right? So it still has to be whole chunks of stuff, but instead of counting numbers, things that I can physically count and hold on to, this is now negative numbers, things that don't really exist. Like I can't hold in my hand -5 things, but I can say that I owe 5 things, or it's the opposite of something. And all of a sudden, when we add integers, subtraction becomes closed. Okay, so that was our big jump in number theory, was to saying this thing has to be closed, so let's just create a system where it does. And the 3 minus 5 is of course the same thing as 3 plus a -5, and that lends us out there at -2. The multiplications also followed mathematical closure, but just like before with the addition that we could only add the same stuff to the same stuff and get the same stuff, we don't have to add the same stuff to the same stuff here, right? The 34 times 2 is of course where we can get, I'm sorry, I covered them up, but where we can get the 2 times 4, which of course gives us 8. But all of a sudden we take 2 times a different number. We take 2 that's not, I'm not multiplying a 1 times a 1. All of a sudden I'm multiplying a 1 times a 10. It just happened to be 3 of them. Sorry, it's not 310, it's 30. Okay, and 2 times 30 is 60. And of course we end up with 68 when we're done. I can do those partial products. I can multiply pieces instead of having to multiply the whole things. So we don't have to multiply the same things. Now, this is commonly the way that we were taught, do the 2 times the 4 and then the 2 times the 3. But if we start to do this in the way that we are going to head our students into the concepts of algebra later on to build that coherence, we can just as easily say, instead of 2 times 4 and 2 times 30, what if I did, oh, get back there. You let me draw now? We can do draw. There it goes. Okay. some reason it was not drawing for a moment. It kept trying to minimize my screen. We can do, oh shoot. Hang on. My computer's going nuts.
Let me know if you need assistance.
Nope. It's just, I hit something and it closed the window instead of moving back. Yes, I know. Technology is so nice when it works.
Is it letting you share your screen again, Andy?
Just one moment. I got to pull that back up.
Okie doke.
And as soon as I get the thing back up, then I'll reshare.
I just have to share while you're doing that, Luella's comment.
Yes.
High day, so things are gonna go irrational.
Oh, yes, that's awesome. Okay. So let's get here and there and share the screen and pull that one back up and go back to slideshow. And let's get caught up with where we were. Okay, but we can look at that as 30 times 2 and 4 times 2. Get the big stuff done first, right? We don't have to multiply the little stuff first. The same way when we multiply in our algebra, we take x times x first. I don't start at the numbers at the back. But if I take 2 times 30, of course, we get 60. 2 times 4, of course, we get 8. But what happens when we got to multiply 18 times 21? Like, how does that thing work? Let me pull off here. Now, I am not doing this, but this should allow me to move the block. There we go. If I take the, oh, I did that one wrong. I got it wrong. Do this one. 18 times 20 is 360. And then the 360, and then the 1 times 18 is, of course, 18, which, of course, will give us 378, not 168. I think I had that 11 originally, and then I changed it to 21 just so I didn't have 1 and 1 on there. But it's okay to go ahead and get the big numbers multiplied first. I multiplied the 10s times the top number, the 10s times the 10s, and the 10s times the 8s first, just to get it out of there. And the 82 and 75, I can look at as 80 times 75 and 2 times 75. And the 75 is kind of nice. What makes 75 nice here? Does anybody have an idea of why I would talk about that being a nice number? Yes, money. Yes. Yes, multiple of 25 is exactly it, Elizabeth. That I gravitate my students to multiples of 25 anytime I can. And we could recognize that 75 is 3 25s. And the 80 times 25 would be 2,000, and 3 times that would give us 6,000. Just doing things like Rebecca said with money, because the 25s are what they're used to. They've got quarters in their pockets right now, right? Let them use that to help them with the concepts of those multiplications. And again, this process then makes that coherent connection to the algebraic polynomials that we do later on. You know, a 5x squared can only be added to another x squared. So a 5x squared and a negative 2x squared will, of course, give us 3x squared. And the negative 3x can only get added to the X, even though it's not in the right spot in that second number, right? We got that X way out at the end after the -7. But we could end up with a -2x, and a +8 and a -7 would leave us with a +1. That same concept, you can only add the same stuff to the same stuff and get the same stuff. Build the coherence in. And if we're multiplying, the 9R times 6R would give us how much? What value would we get out of that? Because I would help my students to see that 9R is exactly the same as 10R minus 1R. And yes, my students do understand that when we have 1R, we don't have to write 1R. You can just write R. They know that from earlier studies, but it's helpful just to see it when they're doing it. So if we see here a 6R minus 4, we can of course get a 60R but now they get a little confused because I was like, wait a minute, I'm multiplying an R times an R. Shouldn't I get an R, right? When we added them, if I add an X squared to an X squared, I can only get an X squared. So why is it that when I multiply these, I can all of a sudden get something different? And it's just to remind them that multiplication and the addition are different. It's okay that they're different, right? We can still do that. Now, if you're going through this problem up in your algebra class and you're going through some of the workbooks, yes, I do like the concept of area too, Luella. I think that's great. But the other thing that you'll often run into is that god-awful FOIL thing. And I know some of you like FOIL. I hate FOIL. I hate it with a burning passion. I don't want students to get locked in. FOIL works great if you've got two binomials. Good. Grid. Yes. Yes. Tell us how we really feel. Yeah. It's one of those that is like the carry and borrow. It's a shortcut that someone just told them, but they don't really know why they're doing it. Right. In binomials, FOIL works great, but if you get trinomials or anything like that, all of a sudden there's no FOIML, there's no middle to put into it. But if we teach this as distribution, okay, yeah, I think that's what she's talking about there. There is the Japanese grid model with drawing lines diagonal one way and then drawing lines diagonal the other way. Luella, is that what you're talking about on that one? No, okay. So more of an area type of thing. Is that what you're talking about? Like Punnett squares, yeah. Okay. So yeah, I don't want to try and draw on here because it's going to start not working again. But yeah, if you put 10R and minus 1R on two sides of a Punnett square and then 6R minus 4 on the other side, you start to see that that those four terms come out just like you would do in a Punnett square in biology. But if we could pull them out to those, that 9 times 6 tends to be the one of them that they're just not comfortable with. They don't like those 6, 7, 8, 9 multiplications. But if I can just remember that 9 is just 10 minus 1, then 10R times 6R and 10R times 4 and -1r times 6r and -1 times -4. Plus, becomes a little bit easier for them because they're easier multiplications. And then of course, the 56r squared and the -36r. So it's the important idea of getting them to understand why they're doing what they're doing with the easy stuff, the counting and whole numbers, to build to the polynomials that we're going to do later on. Okay. But there's one we haven't talked about yet. Talked about addition, we talked about subtraction, we talked about multiplication. They're all closed under the integers. Everything works. But all of a sudden they started throwing this division in and stuff not worked again, right? We ran into problems again. So much like subtraction, if you look at those, you would say, well, wait a minute, under counting numbers, under whole numbers, under integers, division's not closed. Now, if I take 4 divided by 2, of course I get 2, and a whole number divided by a whole number is still a whole number. It worked great. But if I had to take 4 divided by 3, all of a sudden it just didn't work anymore. So we fixed it. We brought in the rational numbers. And so all of our rational numbers are just all of the same numbers we've been working with the whole time, and everything fits. But we recognize a rational number is just a ratio, a comparison of two numbers. We can often think of it as a fraction. It doesn't have to be a fraction, but it is a ratio of P and Q, where P and Q are elements of Z. P and Q are integers, right? And of course, they both can be negative. We tend to not like the denominators being negative, but in the end, it does still work, and it does still fit within our rational number systems. So bringing in the rationals fixed mathematics over the division. The rationals still follow all the rules of the inner categories. They're still closed under addition, multiplication, subtraction. But now we've also made sure that our numbers work and are closed under division. And any rational number added, subtracted, multiplied, or divided by another rational number must also be rational, with one exception. There's one that doesn't work. Does anybody know the one that doesn't work? Okay, what I mean by they are closed means that if you do that operation on a rational number, you have to get another rational number. Okay, so mathematical closure says if I do an operation, I don't change number systems. So a whole number divided by another whole number could possibly still be a whole number. You know, 15 divided by 3 is still 5. It works fine. But if I take 17 divided by basically anything except for 1, all of a sudden I don't have a rational number anymore, right? 17 divided by 2 does not fit in that rational number system, so it's not closed. But if we recognize the rationals, 17 divided by 2 is just 17 over 2. That's a rational number. It worked perfect, right? Any rational number divided by or added or subtracted or multiplied by another rational number has to be rational, except one. There's one exception. What's the one exception? What's the one that breaks mathematics? And it breaks it so far that we've never fixed it. Anybody? Bueller, sorry. Oh, Rebecca did say 0. Wait a minute, is my volume down?
No, she said it in the chat.
Okay, thank you. I'm like, wait a minute, I didn't hear anything. Yeah, thank you, Rebecca. Yes, 0 is the exception. Can we divide 0 by a non-zero number. Is that allowed? Like, can I take 0 divided by 5? Sure, no problem, right? 0 divided by 5 works great. What I can't do is 5 divided by 0. That one doesn't work. And that's one of the things that just, we've not been able to fix it. It doesn't work. Okay. So adding and subtracting rationals are really easy if we use good, normal, rational numbers, and the denominators are the same because they still follow that same concept. You can add and subtract the same stuff from the same stuff and get the same stuff. So 5 ninths and 2 ninths is, of course, 7 ninths. It works just fine. And 5 sevenths minus 3 sevenths is, of course, 4 sevenths. If I add ninths to ninths, I have to get ninths. If I add sevenths to sevenths, I have to get sevenths. And of course, we can decompose. So we said here, if we have 16 3/5 plus 27 4/5, well, I decompose that 16 and 27 into 10 and 20 and 6 and 7. Now I can also decompose the 6 and 7 to make a nice easy 10. But we see the 10 and 20 gives us 30 and the 6 and 7 gives us 13. And together those give us 43. That's a nice easy one. I don't have to worry about the fractions. I'm going to deal with those later. But the 3/5 I left there, but that 4/5 I decomposed. I changed it. Just because I want to find something easy. And anytime I can find a rational number where the numerator and denominator are exactly the same, life gets a lot easier, right? That's 1. So 43 plus 5/5 is 1, that's 44. And of course, we just have the 2/5 left over. So if they understand that basic concept in the early standards, in how do I add whole numbers, that works exactly the same for the rationals. Okay, I am going to pick up the pace here a little bit because I realize I'm behind, but we're doing good. So just like the integers, we don't have to have the same things in order to multiply them. Multiplying is just fine. 4/3 times 5/8 is just 15/32. You multiply the numerators, you multiply the denominators, you're done, right? That's it. But the 6 1/3 times 9 1/4, that all of a sudden starts to get a little bit trickier. Now, I did show on here how you can decompose the 6 into 18/3. I didn't have enough room to write it all, but you know how to do that. The 6 becomes 18/3 plus 1/3 gives you 19/3. And the 9 decomposes into 36/4 plus the 1/4 would give you 37/4. Now, once we start dealing with this, 19 times 37, all of a sudden not so nice and fun. And most of the students are like, this sucks, I don't want to do this. But if you can make the connection that 19 is simply 20 minus 1, right? But if you do the 20 multiplication, most of the students think that's really easy. 20 times 37, that's 740. That's not a difficult multiplication, and I've got it. And 1 times 37 is really easy, that's 37. So all I have to do is end up with 740, take away 37, and end up at the 703. And the 3 times the 4 gives us 12. But 703 can be broken up. Okay, now most students are not going to recognize that 696 is divisible by 12. But if they do that division, they'll find that 703 divided by 12 does give them 58 and some weird decimal thing on the end type of stuff. But if they recognize that's just 58 and something, it makes it easier to find that decomposition. 58 times 12 is 58 times 10, and 58 times 2 put them back together, that is 696. And the leftover is 7. So it's making the connections early to make the later ones easier. And the multiplication by ones, we know, and we highlight this and we talk about it a lot. If I'm going to say that 9/4 is equal to something, I have to do something that allows it to be equal. What's the number I can multiply to make something equal? Multiply by 1. I just happen to use the version 5/5. Or the 2/5, I can multiply it by 1. Just happen to use the version 9/9. So of course, this ends up as 20/45. And this one over here would end up as 18/45. What that allows us to do is then convert our denominators, because we can't add 4/9 and 2/5. It's not possible. You cannot put them together. They're different things. But if I make them both into 45ths, now I can add them, because now I'm adding the same stuff to the same stuff and getting the same stuff. At which point we'll get 38/45. It's often that we put stuff into the calculator. We talk to them about how the calculator on the GD test allows you to do fractions, and they all just want to jump into it and do the fractions really easy on the calculator. But they say, wait a minute, I added 9ths to 5ths and I got 45ths. You told me I can only add the same stuff to the same stuff and get the same stuff. Emphasizing that multiplication by 1. Yes. Thank you, Lindsay. Okay, but what about the division? Okay, the division, if our numbers divide easily, like 9 divided by 3 is 3, and 10 divided by 2 is 5, we divide fractions literally exactly the same way we multiply them. It's perfectly the same process. Divide the numerators, divide the denominators, you're done, right? Nice and easy. The problem is what happens when 5 isn't divisible by 3 and 7 isn't divisible by 8. They don't make nice numbers. But if we recognize we can still do this, this does work, and this is a correct answer. 5/7 divided by 3/8 is 5/3 divided by 7/8. That is absolutely 100% correct. It's just god awful ugly, right? But if we do that back, as Lindsay said, emphasize that multiplication by 1. Take this fraction, this 5/3 divided by 7/8, and I multiply it. Oh, sorry, didn't mean to move that one. You want to move. I multiply that by 3/3. The 3, because of that 3 in the numerator of the big fraction, that gives you the 3 in the denominator of the numerator. I know it's weird to say all those words, but I don't want to have 5/3. I want to just have 5. So I multiply it by 3. But if I multiply by 3, I change. So I multiply by 3/3. And again, if we multiply this by 8/8, the 8 in the denominator takes out the 8 in the denominator of the denominator. And if we recognize that these divisions simplify this, that first fraction ends up right back at 5/7, the exact place it started from. Our 5/7 is still 5/7. But now we are no longer dividing. We are now multiplying, because we multiplied everything. But if we look at those second 2 fractions, the 3 was in the numerator was gone because it canceled with the 3 in the denominator of the numerator. And so we get 8/3, and we recognize, wait a minute, that's just multiplication, but I took the second fraction and flipped it over, right? They all know that rule. They will immediately jump onto it. oh, if I'm dividing fractions, I take the second fraction, flip it upside down and multiply it. None of them know why they do that. This is why. And then of course it becomes a lot easier because we get the 40/21, which is 1 and 19/21, if they want to change it to a mixed number. Show them this, help them to really take the time to understand why we're doing what we're doing, and everything becomes a lot easier. So we expand those categories to rationals, everything works. Those early civilizations, the Greeks and other people, I'm focusing on the Greeks because they're the ones that wrote the most about it, but the Egyptians and the Spanish and the Chinese, they all did this too. They understood this, but the Greeks called these numbers commensurate. We could commensurate the numbers, okay? I know that seems confusing, but if you go through it a couple of times and just let them see it, that it always works, it helps that helps them to see why that works. And yes, there are multiple proofs of that. So the Greeks said every number created by the gods is rational. There is no numbers that aren't rational. That is the end all be all, we're done. But then we ran into this guy. And we finally get to pi, right? The Greeks took this circle and they said, well, what happens if I take the distance around the circle, the circumference, and I divide it by the diameter and I look for a ratio there? And they started seeing, well, wait a minute, it seems like it's around 3. And it keeps coming up around 3. What the heck's going on? It doesn't matter how big or how small my circle is. It keeps coming up the same number. Why is it doing this? And why can't I figure out what the number is, right? They couldn't make this commensurate. They could not make a good fraction out of it, even though they said, hey, it's a fraction. It's right here. This is a rational number, C divided by D. But it's not coming up rational. It's not, I can't get a number out of it. So obviously either the C or the D is wrong. Something's going wrong with this. So along the way, we get famous dead guy in mathematics, Pythagoras. And Pythagoras is really big, important guy in Greece. Everybody loves him. He's got these groupies that hang out around him. They're called the Pythagoreans because they love Pythagoras. And this is how you learn. You just hung around smart guys until you figured out what they were doing. And Pythagoras and his Pythagorean groups said, hey, wait a minute, I found out something. If I take a triangle, and I know we were talking about pi in a minute, we'll come back to it. But if I take a triangle that happens to be a right angle, has this 90 degrees, then the square of the sides has to equal the square of that longer side. And we're going to give it this fancy weird name. We're going to call it hypotenuse, right? So the hypotenuse is that longer side. So in this particular triangle, what is that other side? You guys all know this when you've used it a lot. What is the hypotenuse in this particular triangle? Yeah, it's 5, right? This is the 3, 4, 5 triangle. And of course, they're all hanging around going, oh, how smart are we? Like, we got it. This thing is a rational number. I got 3 and 4, and I get a rational number 5 out of it. Everything's working. Things are great. Then came along one of Pythagoras's groupies that hung out with him. And he said, wait a minute, what if I make those two sides 1? Okay, what if they're not 3 and 4? What if they're just 1? And they started out with this square root of 2. They knew this a squared plus b squared equals c squared thing has to work. So if a and b are both 1, 1 squared is of course 1, and 1 plus 1 is 2. And if 2's got to equal c squared, then c's got to equal the square root of 2. And fantastic, we found this other rational number. Things are great. Then Hippasus comes along. And Hippasus goes up to his big guy, like he's one of the Pythagoreans, he's hanging out with Pythagoras. And he goes up and he says, hey, guess what? All numbers are rational. I just broke it. I'm gonna prove to you that this can't be rational. And so he said, assume that it is rational. Assume that square root of 2 is just a over b. But we're gonna make sure that a and b are mutually prime. There's no common factor in them, or we could divide that factor out and just make it less anyway, right? So we've got this ratio a over b and everything's great. Okay. So if we do this, we multiply both sides by b, then we can say b times the square root of 2 is a. Great. Square both sides. Square root of 2 times b is 2b squared. And that has to equal a squared because a times a is a squared. But hey, wait a minute. A has a factor of 2. A has 2 times something. That something happens to be b squared. But it's got a factor of 2. Therefore, a is even. That's great. But if a is even and b can't be even, because if b was even, we could have divided by 2. They wouldn't have been mutually prime. So b has to be odd, right? That has to work. So what if we just rewrote these? The definition of even, and they knew this, was 2 times a number. So they said a is 2 times p. And the definition of an odd is 2q minus 1, 2 times a number, subtract 1, that's going to be an odd. If I plug those into that 2b squared equals a squared, I end up with a final equation that says 4q squared minus 4q plus 1 equals 2p squared. That tells us that an odd number has to equal an even number, because 4q squared minus 4q plus 1 has to be odd. It cannot be even at all. It has to be odd. And 2p squared has got to be even. Can't work. Contradiction. Square root of 2 is not a rational number. Can't work. They hated this so much. It broke their minds so badly. They put a grave outside their building and said, Hippasus is dead to us. He has to go away. We don't want him around here anymore. He broke our perfect number system. It doesn't work. But whether you like that it worked or not doesn't matter. They found the irrational numbers that can't be commensurate. So if we get back to the circle, Archimedes, another famous dead math guy, he's Greek, said, okay, wait a minute, what if we could take a circle and make it into something that we can measure and get an actual real perimeter for? So we started taking a circle and putting things that we can find perimeters for inside it and outside it. Now I showed here an inscribed square and a circumscribed square. It's where a square is inside and a square is outside. I also did it with a pentagram and a hexagon. He didn't do this. He started at hexagons and started working his way up from there. And this was one where we're going to do it, but we don't quite have enough time. You can do this one on your own or take it and give it to your students. Have them try and figure out what the values are for these. We know that it's got to be bigger than the square on the inside, but smaller than the square on the outside, or bigger than the hexagon on the inside and smaller than the hexagon on the outside. If we actually calculate those out, we'll see that the square on the inside's got to be about 2.83 and outside is 4. The hexagon on the inside has got to be 3 if the diameter is 2. Okay, if that works. So Archimedes did this. Some other groups did this. Ludolf van Keulen did a polygon with 2 to the 62 sides on the inside and outside. It took him 25 years to calculate this out. And he actually got pi to an accuracy of 35 decimal places. It's actually engraved on his tombstone. You can go to Denmark and see his tombstone and see pi written out. Okay. So realize how long this took him and how accurate he got. There are a couple of videos here that you will get this thing, so you can go look at these videos later. The first video is from a guy, and he runs a thing that he calls Veritasium. The element of truth is where he pulls that. And he shows a video of how we now calculate pi, because we don't do that inscribing and circumscribing of polygons anymore. That just takes too much time. We can actually calculate pi really easily using some calculus that Newton and Leibniz invented. The second one is from the Scientific American, and it talks about how accurate do we really need to be with pi, right? We go to our GED test, and right on the GED formula sheet, it says pi is approximately 3.14. So they're saying use 3.14. Do we have to use 3.14? So from NASA's Jet Propulsion Laboratory, these are the smart guys and girls. Let me put that, the smart people. And these are the people, including people that helped get people to the moon. If you've watched the movie Hidden Figures, those groups that helped get people to the moon and get our spaceships to Mars to be able to put rovers on Mars, they have gone through and said, oh, you know what, when we want to put somebody on the moon, it takes about 6 decimal places of pi, and we've got it, and we're not going to miss the moon. If we think about the size of our entire universe, yes, only 6, and we can get somebody to the moon. That's how accurate we need to be. But if we think about our known universe, this is a picture from the James Webb Telescope looking at galaxies far, far away. We've estimated the size of the known universe. That doesn't necessarily mean that it's not bigger than this. This is all we know, as about 46 billion light years. If we take a diameter of 46 billion light years and calculate the circumference of that known universe using pi with 38 digits, that's only 3 more than Van Coulen's approximation, right? We can calculate the circumference of the entire known universe to an accuracy the size of a hydrogen atom. We can know how big the entire universe is and only have an error the size of a hydrogen atom. We don't need pi to billions of places. We've done it. We put it in calculators and computers and calculated pi out to billions of places. There's even websites you can go to say, where's my phone number in pi, right? It'll tell you where it is. But the entire universe can be measured to the size of a hydrogen atom with just 38 digits. That's all. So how accurate do we actually need to be with this pi number? What if we use 3? What do you think our error is? What percentage error from the known approximation of pi is 3? Anybody? Okay, we're going to move on because we're going to run out of time. This is an error about 4.5%. So 4 parts in 100, not that big of an error. For most of our stuff that our students are going to be doing on the GED test, if they use 3 for pi, they're going to be able to find the answer, especially on a multiple choice, right? You can use 3, but just know that 3 is a little bit too small. So I calculate with 3, go a little bit bigger than that and pick that one, right? It's only a 4% error. It's not that much. If we use 3.1, that error drops to only a 1% error, okay, a 1.3% error. So we're getting more accurate. We have less of an error in there. If we go to 3.14, we now only have a 5/100ths of a percent error. That's 5 parts in 10,000 error on this. That's why they often say, we'll use 3.14, because the error is so small, it's not going to matter when you're actually calculating something out. If we go all the way to 3.14159, our error is 800 thousandths of a percent. That's where we start talking about the more decimal places we go, the more accurate we get. We can all of a sudden start measuring huge things to incredible accuracy. That measuring the universe to the size of a hydrogen atom, we don't know that the universe is exactly perfectly 46 billion light years across. That's an estimation, right? So if we're getting that, we're getting way more significant digits or way more accuracy than when we have. Yes, this is why it makes only 6 digits. Those 6 digits put them within 800 thousandths of a percent error. So when our students are using pi, just remember most of the time 3 is going to work, right? Don't get too caught up on this 3.14 thing. It's nice. It's not that hard to calculate with, but gosh, I like 3. 3 is just a lot easier. And especially for any test questions you're going to get on the GD or HiSET, it's probably close enough. I used to work for the Forest Service. When I was in college, I worked for the Forest Service during the summers, and we had to estimate trees and figure out how much lumber is in a tree. If we cut that down, take it through a sawmill, how much houses can we build out of it? Absolutely, 3 was well within our tolerances, right? We didn't have to be super cute and get this 3.14. 3 was good enough. So last part here, and it is time to go, so it's time to wrap it up. There is a proof on here. I'm not going to include it just because it takes too long, and it does take a little bit of calculus, but we can prove that pi is irrational, very similar to the way that we proved that square root of 2 is irrational. We do a proof by contradiction. We assume pi is rational and show it can't. Okay. Our easier thing is to say, as much as we want to square the circle and make it into a polygon, we never can. No matter how many sides you get, it's still not perfect. Okay, so it's always going to be that one. So if we include roots and pi and some other numbers, rationals and irrationals, they're separate. Remember in our picture how they were not part of the looped ovals or the strand of categories that built up to rationals. Rationals, irrationals are completely different from each other. So how do we make all this work? We said, fine, we're going to throw the 2 of them together and call it the reals. Okay, so the real numbers are just everything that is rational and irrational. But of course, we still got the problem we talked about earlier. We cannot divide by 0. A lot of people call 0 undefined. It's actually both undefined and indeterminate. Okay. That means if I divide a non-zero number by 0, it can't work. It's saying what number times 0 is equal to 0, and there isn't any. There's no number that makes that true. But if I look at the fraction 0 over 0, that's not undefined. It's indeterminate, because 0 over 0 could equal 1 because a number divided by itself is 1. But 0 divided by 0 could be 0 because 0 divided by any number is equal to 0. It fits both those 2 rules. And so he said, since it can fit both the 2 rules, it doesn't fit any rules. And it's just indeterminate. We just have to throw it out. And of course, that last one that I just threw down there in the bottom, the square root of a negative number is not real. Okay, that is a number that does not work. It does not fit in the real numbers, as no number squared can ever be a negative number. A positive times a positive is a positive, and a negative times a negative is also a positive. So I can't take the square root of a negative number. So the only question we could run into on the GD test, and I've seen this in some of the prep materials, is to say, what is the domain and range, or what are the values you can plug into this function, and what are the numbers you can get out of this function? And we can say that f of x equals the square root of x minus 3 completely works. It is fantastic. There's no problems with it as long as x is greater than or equal to 3. But if x is less than 3, it breaks. It becomes a complex or irrational number, or sorry, imaginary number, and the imaginary numbers just don't work. They cannot be reconciled back into the reals. It's the one thing that truly breaks math that doesn't work. So each of the number categories has a basic structure. We can provide coherence by building these categories into the next category, help your students to know the foundations, move forward to new material, not so difficult. Okay, that's it. Build your way up. Anybody that has any questions, if you ever have anything you want to talk about and want to discuss these or look into them in more depth, happy to talk to anybody anytime. If you want to get in contact with me, go right ahead. And other math teachers on this thing are great at this too. Talk to the other people on here. They'll give you hints as to how to build this coherence together as well. Okay, awesome. Very happy that you were all here today. I wanted this to be a little bit more discussion. Unfortunately, it wasn't. It was more me talking, but it still worked. And I'm very happy that you were all here. Do remember, okay, remember coming up in August is Summer Institute. Summer Institute is going to be live. We are going to be in person at Waite Park, Minnesota. We are still looking for presentation proposals for Summer Institute. Right now, we've got very, very few. Please, please sign up to present at Summer Institute. We need more people up there and giving us some good stuff to work with. If you have any questions about Summer Institute, let me know. But Summer Institute proposals are due the end of this month. So we have another couple of weeks, and then we're going to start going through them. Okay, anything else anybody wants to ask about or talk about before we go? Oh, thank you very much, Marisa. There's the link for the call to proposals in the chat box. Please go into the chat box, grab that, submit a proposal. Love to have you up there. By the way, I am the committee chair this year, so that's why I'm begging you so bad. I don't want to be up there by myself.
That's awesome. Thank you so much, Andy. This was great.
Welcome.
Lots to think about.
Yeah, it was a fun one to put together. Go back to some of those old things that the Greeks thought about, and it's like, you know, my father-in-law talks about how we are incredibly wealthy in this country. We are richer than King George was when this country was founded. We have flushing toilets. King George never had flushing toilets. We have air conditioning. King George never had air conditioning. I can get on an airplane and fly to another country. He could never do that, right? We are richer now than he ever was. Going back and thinking about this stuff of what the Greeks knew and how much more we know now than what they knew, it's just incredible. It's amazing. So